All right. Good afternoon, everyone. Today we are pleased to have Daniel Perucci from the University of Buenos Aires. Daniel is going to talk about the extension of Putinar Positivstellensatz to non-compact sets of cylindrical type.
Okay.
Daniel?
Well, thank you very much. Thank you everyone for joining, and please feel free to interrupt at any moment, any questions, comments, whatever. Okay, so I'm going from the very beginning of the sum of squares theory. So if you know about this, you may get bored at the beginning, or maybe all the talk, I don't know. So we have a polynomial with real coefficients in n variables. The typical question is, if this polynomial is non-negative, does it mean that it's a sum of squares of other polynomials? So SOS means sum of squares all along the talk. Well, the answer is no. The first explicit counterexample is this Motzkin's polynomials, which is known in 1977. Well, it's this polynomial here. It's non-negative everywhere in R2, but it's easy to see that it cannot be written as a sum of squares, just some identity. I mean, if you try to write this as a sum of squares, then you start looking at the coefficients, and in the end you get that you cannot. So first counterexample, but is there any hope to, I don't know, to save the situation? And the answer is yes. If you have some extra information, for instance, if you are working with univariate polynomials, then it's the same, it's equivalent to be non-negative or to be a sum of squares. The same if you have polynomials of degree 2, and the same if you have a bivariate polynomial of degree 4. Okay, in all these three situations, which are expressed in terms of degree and number of variables, this is the whole list. I mean, this is the whole list of situations where we have an equivalence between being non-negative on Rn and being a sum of squares. There is an extra case, less known or less famous, let's say. This is the case where we have a polynomial in at least two variables, and you put one of them aside and you look at the degree in the rest of the variables from x2 to xn. And if this degree is 2, still holds that the polynomial is non-negative if and only if it's a sum of squares. Okay, there is no restriction on the degree of this polynomial with respect to x1. Well, it's easy to see that if the polynomial is non-negative, then this degree has to be an even number, but nothing besides that. I mean, it's just this. So this is the situation for polynomials which are non-negative everywhere. But what can we say for polynomials that are non-negative, not on the whole space Rn, but in a subset S, which is a basic closed semi-algebraic set. So this is the set defined by the inequalities given by polynomials G1, Gs. All of them are polynomials with real coefficients in n variables. So F, we want to say something about polynomials which are non-negative here. So first result, one of the most important results in this theory is Schmutgen's Positivstellensatz. And it says the following: assume that S is compact and assume that F is positive on S. I mean, it's not enough to be non-negative, it has to be positive. Then F can be written in this way. It's a sum of many terms. You have one term for each subset of the set from 1 to S. I mean, in a way, it's one term, sorry, for every possible election of some of the GS, some of the polynomials G, okay? So you make your election, and then you have one term which is a sum of squares times the product of the GIs you have chosen, okay? So it's clear that each of these terms will be non-negative on S because they are sum of squares times sum of the GIs, and all of them those are the polynomials defining S. Therefore, each term is non-negative on S. This is a certificate of the non-negativity of F on S. I mean, because it's written in this way, which makes obvious that f is non-negative on S. Okay, it's sum of squares times products of the GIs. Well, there is something a little bit like annoying in this result, which is that we require that f is positive, and then we only certify that it's non-negative. I mean, if we would, in an ideal world, we would like to that this holds also if f is non-negative, but unfortunately it doesn't hold, and we will see an example in a minute. There is some other very important result here. It's Putinar Positivstellensatz, and it's, let's say, it's a stronger conclusion under a stronger assumption. Before we have the assumption that S was compact, now we will have something a little bit different. I will explain in a minute. We have these question marks here just to say to indicate that there is some hypothesis that I will explain in a minute, and the same other hypothesis that f is positive on S. And under these two assumptions, we have a new way of writing f as a sum of using sum of squares, but this time it's much simpler. It's sum of squares plus sum of squares times G1 plus dots sums of squares times GS. So in a way, it's a particular case of the expression we had before, because before we had one term for each possible subset of the set 1 to S, and now we are only taking care of, I mean, taking into account subsets of cardinality at most 1. I mean, we have only one term for the empty set, and then we have one term for each election of one polynomial. Okay, so the expression is much simpler, and you can think that it's an expression as the one in the previous slide, but now many sum of squares are 0, so they just don't appear there. Okay, so this, as I said before, as a summary, is a stronger conclusion under a stronger hypothesis. So what is this hypothesis? So we consider this set M. This set is the set of all polynomials that can be written in this way, using sum of squares and the GIs in this way. This set is called the quadratic module generated by G1 GS. It's a set which is closed under addition. It contains squares, and you can multiply whatever. It contains 1, and you can multiply whatever you have by a square, and it will still be there. This set, this quadratic module, is said to be Archimedean if there exists a positive or non-negative quantity, n, real quantity, such that n minus the sum of the variables belongs to M. Okay? Notice the following, that any polynomial in M will be non-negative in S, as we said before, because the way they are. And saying that n minus the sum of the squares of the variables is in M implies that this polynomial is positive on S. Sorry, it's non-negative on S. But then this means that the sum of the squares of the variables is bounded by n on S. Okay? So that this implies that the set S is bounded, and since it's clear that it's closed, we conclude that it's compact. Okay, so as I said before, the hypothesis in Putinar's Positivstellensatz, which is that the module M is Archimedean, is stronger than the hypothesis in Schmudgen, which was just that S is compact. But this is stronger. This implies that S is compact. Okay, this is well, let's see that the condition. Let's show this example to show that the condition that f is positive is really necessary. It's not possible to extend this theorem in full generality for just asking f to be non-negative. We have this example. Imagine that S is defined by the inequality given by the polynomial 1 minus x squared raised to the cube. This is just the interval minus 1, 1. And then we have the polynomial f, which is 1 minus x squared, which is non-negative on S. But it's easy to see that it cannot be written as a sum of squares plus a sum of squares times the g1, I mean, the only g we have here. Any polynomial that can be written in this way, if it vanishes on 1, then it's easy to see that 1 is a root of multiplicity, at least 2. And this is not the case for 1 minus x squared, so we cannot have the identity there. And let me say that this example, it works as a counterexample for both polynomials, because here the set S is defined by just one polynomial g. We only have g1. So having every subset of 1 to 1 of cardinality at most 1 is the same as having every subset of this set. So it's an example for both results. There is something annoying about this, the way that S is defined, because it's 1 minus x squared raised to the cube. But well, here it's very simple to see that, well, the first thing you do will be to just delete the cube. It defines the same set. But this is not so clear how to do if you are working in polynomials in many variables. It's, for instance, when you have two inequalities, let's say A non-negative and B non-negative, this is equivalent. You can replace both by AB non-negative and A plus B non-negative. And once you've done that, I mean, you need to do something to rediscover that you have done this and you go back. So in general, I mean, if you have many polynomials defining the set S, you just take them as they are and you do what you can. I mean, but it's not, there's no easy way to produce a simpler description, or there is even no notion of what is the simplest description you may have. Okay? Well, so what about degree bounds? I mean, I won't talk about degree bounds in this talk, but just I want to mention these papers because they are very important. And I mean, both results are about a way of rewriting the polynomial f in a way that makes obvious that it's non-negative on S, and it involves many terms. Are there degree bounds for these terms? And well, the answer is yes. For Schmutgen, we have this paper of Schweighofer. And for Putinar, we have first a paper of Nie and Schweighofer, and very recently a paper of Baldi and Muren, which improves on the previous one. Okay. Well, this is, so far I'm talking about, let's say, the classical situation, which is when S is compact. So what can we say if S is non-compact? Well, first we can do this slight modification of Motzkin polynomial. So the first part, I mean, all these terms here, sorry, all these terms here till here, this is just Motzkin polynomial homogenized, and it turned out to be non-negative on R3, but it does vanish. It vanishes on 6 lines. The zero set is the union of 6 lines. But then you can add any positive quantity k, and well, it will obviously be still non-negative. Moreover, if k is positive, it will be positive because it's non-negative plus positive, but still not a sum of squares. So there is, I mean, the fact that it's not a sum of squares, it does not have to do with the fact that the polynomial maybe it vanished somewhere, or maybe it's very close to 0 somewhere. No, here you can make the minimum as big as you want, and still it won't be a sum of squares. Okay, and why I'm talking about this case as I mean R3 is we can think of R3 as the same as we were talking before when it's defined by no polynomial. Okay, there is no inequality here. So when we are in all these expressions we were looking for, we will have one term for each possible subset of the empty set. So we only have one term which corresponds to the empty set, and this is just a sum of squares. So I mean, writing polynomials non-negative on R3 as sum of squares is a particular case of the other theorems we were looking before. Well, but we see here that it's not possible in general, and not even if we add the condition that polynomial is positive, still it's not possible to write them as a sum of squares. There are some more negative results. They are by Scheiderer, and he gives two cases. First case is when the dimension of the semi-algebraic set is at least 3. This is both in the case that it's compact or non-compact. It works no matter that. And also if we are working with bivariate polynomials, but S contains an open cone. I mean open cone, I mean full dimensional open cone. Then in any of these two situations, it can be proved that there exists a polynomial which is non-negative on S, but cannot be written in the way we were considering before. I mean, as a sum of many terms, one term for each possible election of the inequalities, and sum of squares times the product of the inequalities. Okay, so if the set S is like this, dimension at least 3, or inside R2 with an open cone, no hope to have a full theorem saying that any non-negative polynomial can be written in this way, or for any non-negative polynomial we have a certificate of non-negativity using sum of squares. Well, so we need to look for, or after this, then the attention is set on sets of dimension at most 2 and with no open cones, and we find the strip. The strip on R2 is just this strip here. It's defined by the polynomial 1 minus x squared non-negative, and there is no condition on y can move freely, and you see that there has dimension 2 and it has no open cone inside it. I mean no full dimensional cone inside it. And it was proved by Marshall that any polynomial which is non-negative on S can be written as a sum of squares plus a sum of squares times the inequality defining, I mean the polynomial defining the inequality of the strip. Okay, so this is on the very contrary. It's like the best possible situation ever. Not only positive polynomials in this set admit the representation we are looking for, also non-negative polynomials admit this representation. I want to say something, I want to stress something I forgot in the previous slide, is that here the conditions are set on the set S, okay? No matter how it's defined. I mean, S can be defined by these polynomials or maybe by some other polynomials, but if the dimension is 3 of its inside R2 and contains no open cone, that only depends on S. And in this case, we have this result. And here, it's not just the set S which matters, it also matters the way it's described. I mean, if we change 1 minus x squared, for instance, if we change it by 1 minus x squared raised to the cube, as we did before, then the set doesn't change, but the result is not true anymore, okay? So there is something subtle there. It's sometimes the results are on the set, and sometimes the results are or depend on the polynomials defining the set, okay? Well,
sorry, Daniel, one question.
Yes.
Before you go on. So if we replace, so looks like S must be a basic closed semi-algebraic set. So in the Putinar representation, if we replace S by any semi-algebraic set, not necessarily basic. Does it still work?
So, I mean, if you, let's, for instance, imagine you are working with a union of two okay, no, there is nothing known for that case. Yeah, no, it's just for basic closure semi-algebraic sets. Okay, so this strip result was generalized to many similar or somehow similar situations. We have half strip, union of strips, and these are inside R2. Obviously, they don't have this open cone, and also inside R3 to a cylinder over the unitary circle. Okay, this has dimension 2. We know that if the dimension is at least 3, then it doesn't work anymore. But this has dimension 2, and also it's true here that every polynomial non-negative here can be written in this case as a sum of squares plus a sum of squares times the equation defining the circle. Okay. Well, what else is known? Well, for the case of univariate polynomials, the whole situation is more or less clear. When is it true that given a semi-algebraic set, basic semi-algebraic set defined by polynomials, inequalities, when is it true that a non-negative polynomial can be written in this way? And also there are many results, not completely covering every possibility, but there are many results for sets of dimension 1 and 2. Well, now let's go more to the topic of the talk, which is non-compact sets of cylindrical type. The first result in this area or in this direction, I would say it's this by powers. So we have S, which is defined by, as before, by many inequalities in Rn, and we make the assumption that S is compact. But now we want to certify the negativity of a polynomial in a cylinder. So this is S times R, okay? So we consider polynomials with one more variable, which is this variable y. So f is a polynomial in variables x1 to xn and y. The g's, g1, gs, are only polynomials in the variables x1 to xn, okay? And the condition is that if we have a polynomial f, which is positive in the cylinder, s times r, and we have some extra condition, which is that f is fully emic on S. Well, what does it mean? Fully emic means if we consider the polynomial f as in a way, we distinguish the variable y and we consider it as a polynomial in y, as a univariate polynomial in y. And if the degree of this polynomial is m, then its leading coefficient will be a polynomial in x1, xn. And we ask that this leading coefficient does not vanish on S. Okay, in a way, it's saying that whenever we specialize the variables x in a point of S, the degree in y doesn't drop. Okay, this is the condition of being fully emic. Well, under these two assumptions, she gets this result says that f can be written as before. I mean, in a sum of many terms, one term for each possible election of the inequalities, and each term is a sum of squares times the product of the GIs. Now the variable y on the right hand side only appears in the sum of squares. Okay, because I mean f depends on y, so it has to be y has to be present also on the right hand side. Well, it is in the sum of squares. Okay, and again, this is a certificate of the non-negativity of f on the cylinder. Actually, the result of powers. I'm presenting it here in this way for simplicity, let's say, but it's a little bit stronger. She can also consider cylinders of type F times U, where U is not all R, but non-compact, closed, basic, non-compact, basic closed semialgebraic set of R. Okay, a union of intervals and points, but non-compact, and it has the theorem has provides a certificate of non-negativity using sum of squares. So it's a little bit more than what is written here. And I want to say something about the proof because it's, well, I want to say something about the proof. The idea of the proof, it's very natural, is we know that the theorem holds for each, if we cut the cylinder with slices, then on each slice we get a compact set. And on each of these compact set, we know that the theorem already holds because the Schmidtgen theorem is exactly this theorem for one of these slices, okay? So the proof goes like this, okay? Let's cut the cylinder with many slicers, one slice for each possible value of y, and on each slide produce such a representation, but not in any way. Let's do it in some clever way. So in the end, all these representations can be glued together to obtain a representation of F that works on the whole cylinder. Okay? This is more or less the idea, and maybe, well, right now it's a little bit mysterious how this is done. In a minute, I will come back to this and I will explain better. I want to say that this is, I'm tempted to say that this is Schmidtgen theorem, Positivstellensatz for cylinders. The only extra hypothesis here is that the polynomial f has to be fully emic, but this is necessary. Let's see if we remove this hypothesis, then the result is not valid anymore. We have this example. The example is very concrete. Positive polynomial on the cylinder that cannot be written in the way we want, and the reason is, you can see, it's not fully emic. Here the degree in y is 2, but the leading coefficient vanishes on the set S. Okay. So the extra condition is really necessary. It's not something created for the proof. It's something that it's necessary. Okay, there is some other result which is a little bit different in this sense. So here now, this is the only slide in the whole talk that the polynomials G1, Gs depends on the new variable y. So now the set S is not really it might be a cylinder, but it's more like a subset of a cylinder. Okay, let's see how it is. So the set S is defined by these inequalities G1, Gs. Now these inequalities depend on the variables x1 to xn and the new variable y. This is a subset of Rn plus 1. The condition, there are two conditions on this in this theorem. The first one is that there exists a positive quantity n such that n minus the sum of the squares of the coordinates lies in the quadratic module we introduced before. So this is this would be like the condition for Putinar, but except that the variable y is distinguished and it's not here anymore. So we only want n minus the sum of the squares of the variables x. There is, at this point, there is no condition on y. So since this polynomial n minus the sum of the squares of the coordinates y x is in M, it has to be non-negative on M, on S, sorry, on the set S, and therefore the variable, the the sum of the squares of the x is bounded in S. And this implies that S is contained in a cylinder, which is the ball of radius square root of n times r. Okay, so it's much more flexible, the result, because it's not a cylinder of S times something. It's more like a subset of a cylinder. Okay, and there is some other condition which is, it can be summarized as good behavior on fibers. But now, if you remember the previous slide, the idea was to cut with slices of the cylinders, specializing the variables y. Here, the idea is the opposite. It's to specialize the variables x and let y move freely. So we have lines, we have many lines. And the condition is on the polynomials G1, GS, once for each possible specialization of the x. I mean, on each possible fiber, when you specialize x, we need that the polynomials G1, GS are good enough so that any non-negative polynomial, univariate polynomial, because we have already specialized, can be written using sum of squares, blah, blah, blah. Okay, I don't want to give too many details on that, but I want to mention the idea that before the other result, we were specializing the variables y, and now we are specializing the variables x. Well, under these two hypotheses, the conclusion is that if a polynomial f is non-negative on S, then, well, it's not the polynomial that can be written in this clever way that certifies that it's non-negative. It's a little perturbation of the polynomial. So to make it precise, the result is that there exists a new polynomial q, which depends on, actually it only depends on y, but the theorem is stated like this, such that for every positive epsilon, the polynomial f plus epsilon q can be written in this way, which certifies that it's non-negative. Okay, so it's the f plus epsilon q is like this little slight perturbation of f. Okay, well, this is the result, and okay, and let me tell.
Sorry, Daniel.
Yes.
Can you explain what was the good behavior on fibers? Can you explain that condition again?
Yes. So, what happened when you evaluate the variables x? So x is x1, xn, and variable y is just 1. Okay. So when you specialize x1, xn to some point, you get a univariate polynomial. Okay. The idea is that for every possible specialization of the variables x, the polynomials defining the set S, this G1, GS, are good enough such that any non-negative polynomial defined in this set, meaning the intersection of S with this line, can be written as a sum of squares plus sum of squares of G1.
And is this something we can check? I mean, how do we check that condition? I mean, this is perhaps this is not very relevant here, but do we have a way to check this condition?
I don't know, to be honest.
Thank you.
Okay. So, well, this is a trained result with Paula Scorciello, also from Buenos Aires. It's more in the spirit of the previous result. So we have again S set defined by polynomials G1, GS in variables x1, xn. So the variable y is not part of the inequalities. So this, and we want to certify the non-negativity of polynomial in the cylinder S times R. So as we said before, this was an it was already known that it was possible to extend Schmurgen to cylinders, but we wanted to extend Putinar, and this is what we did here. Okay, so the second result, which I mentioned at the beginning, which was stronger result, stronger conclusion under stronger hypothesis, we wanted to extend to cylinders. And this is the result. It's exactly the same hypothesis, that the module M is Archimedean, and we need to add the condition that F is fully emic as before, because otherwise it's not true anymore. The same example I showed before works for this counterexample, and under this hypothesis, we extended Putinar to cylinders. I wanna tell you very quickly the idea of the proof. So we have the set S, which is defined by these inequalities, and we make the extra assumption that it is included in this simplex, the simplex having as vertices the origin and the elements in the canonical basis, the vectors in the canonical basis. If this assumption is not satisfied from the very beginning, it's just a matter of doing a linear change of variables and a fine change of variables. So we can always think that the set S is included actually in the interior of this simplex, okay? And we have a polynomial F, which is positive on S times R, on this cylinder. Okay, first step is to do a perturbation of F, but it has to be a very clever perturbation. This perturbation is of this type, F minus H, where H is already somewhere in the module, and in a way such that F minus H is now it's positive in the whole simplex times R. No, before F was positive on S times R, and S is included in the simplex. So we want to extend the region where it's positive. Well, this means that how should this polynomial H be? Well, if we are inside S, it cannot be too big, because we are subtracting something. If it's too big, it will not be positive anymore. And outside S, but still inside the simplex, it has to be negative, so that when we do F minus H, we are actually adding something, and now it becomes positive. This idea of perturbate the polynomial F in this way was already present in this paper by Me and Schweighofer, and was more or less we are following the techniques. Now we have polynomial F minus H, and this is positive on the whole simplex times R, and we do this slices idea specializing the variables Y, okay, as in the result by powers. So, but now the good thing is that we are in the simplex, and in the simplex there are much, before S was some basic closed semialgebraic set, we don't know, it can be very general. Now we have moved to the simplex, and the simplex is very concrete, very rigid, and you have better theorems there. Using Polya's theorem in a clever way, it can be shown that F minus H can be written at each slice, after a specialization of Y, as a sum of many terms. Each term is a positive number, a coefficient here is this B alpha of Y, times the sum of squares, times this other thing here, this product here, which does not depend on Y, okay? So we have three things here. We have this, which is a real number, always non-negative. This, which is a sum of squares in X, actually, in the variables X, and these products. Okay, so let's go let's start with the last one. These things are positive on S, because we are under the assumption that S is in the simplex, is included in the simplex. And it doesn't involve the variable y. So we can use Putinar Positivstellensatz for this polynomial. I mean, the classical, the one which requires that the module is Archimedean, because we have get rid of the variable y. So this allows us to say that this part here are in the module. This is a sum of squares. We multiply by something in the module, stays in the module, and this is a real number, negative real number for each y. But the construction is made in a way such that this depends polynomially on y. So in the end, we have a polynomial on y, which is, I mean, a univariate polynomial on y, which is always non-negative. This means that this is a sum of squares, because we know the cases, we started all this talk with the cases where was the same sum of squares and non-negative, and univariate polynomials was one of these cases, okay? So this can be written as a sum of squares, and finally, this whole expression belongs to the module. And then we have f expressed as h plus f minus h, and they are both in the module, so the sum is in the module, okay? So this is roughly the idea. And I was giving once this talk and Michel Coste was in the audience, and he said, I have a question. If you are doing this because this polynomial is non-negative and therefore it's a sum square, can you do the same in every other possible situation which non-negative means sum of squares? And he was right. And this is, so we got more extensions of Putinar to non-compact situations. So now we have basically one case for each case where we have the identity between non-negative and the equivalence between non-negative and sum square. So degree 2 in many variables, degree 4 in 2 variables, and degree 2 in almost every variable but 1 in any number of variables. And we always need to put one condition which is not exactly the same as fully emic, but it's similar and plays the same role as fully emic. Well, that's everything.
Thank you, Daniel. So we have a few minutes, more than a few minutes for question discussions. Any question for Daniel?
So I have a question. So what are the possibilities for proving such results other than the strip? I mean, other than the strip times something.
Yes. So let me see. So we have these extensions by these people here. And there are also some cases, for instance, if you cut, well, obviously you can do some change of variables so that you can complete this like something like this, where this is some function h of x. This is just a change of variables, so that's easy. But there is also one case which is in this same paper by Nguyen and Powers, which is not just a change of variables, and it is like adding a curve like this, like having this it would be like this curve goes closer and closer to this one, and the set, finally the set S would be this one. You see? And it's also proven there. But I mean, I think that one of the open questions in the area is some full classification, saying you give me your set and I will tell you if every non-negative polynomial can be written in this way or not. I mean, that's open as far as I know.
Mhm.
And also, let me say some other, because for instance, I said before that there were these degree bounds, but this degree bound depend on, well, the degree of the polynomial, some norm on the coefficients of the polynomial, and the minimum value of the polynomial in the compact set. Okay, this minimum value typically is appears as the denominator of the degree bound. Okay, but now what? Because this is because Muthen and Putinar put as hypothesis that the set is compact and the polynomial is positive, so the minimum is positive, right? What happens if you want such, I mean, a degree bound like this in this set, in this sense, where the polynomial can be equal to 0? So you cannot put the degree, the minimum in the denominator anymore. Okay. Is it still open? I mean, is it possible to bound the degree of sigma 0 and sigma 1 just in terms of the degree of f and maybe the, well, not the, I mean, before, so the other bounds involve the norm of the coefficients and the minimum. Norm, they are typically the norm of the coefficient is multiplying and the minimum is in the denominator. But this makes sense because if you change f by a scalar multiple of f, then this quotient is the same. The quotient remains the same. Now we cannot use the minimum anymore, so it seems that we should also not use the norm of the polynomial anymore, because then you can just cheat multiplying by the scalar. Okay, so can the degree of sigma 0 and sigma 1 be bounded just in terms of the degree of f? This is not known. There are very few results in particular cases, like if the degree of f in the variable y is at most 2 or something like this. But then exactly that. If the degree of y is at most 2.
But if such a thing is true, that you can bound it only in terms of the degree, so it's an uniform bound, then wouldn't that imply that this theorem is true over arbitrary real closed fields by transfer principle? Because then you have to only look at finite, I mean, the sigma 0, sigma 1 is going to come from some bounded dimensional space of polynomials, and the non-negativity. So this statement here would be a first order statement once you. I mean, we can talk about it later.
Yeah, well, I mean, I guess it's not that simple because people has been thinking of this, but right now I cannot answer why not.
I mean, is it known that this is not, you need really some kind of Archimedean property for this theorem, and it's not?
Well, Putinar Positivstellensatz doesn't work in extensions.
Yeah, but this last one of Marshall.
Well, but it's a Putinar, I mean, it's a Putinar type representation, so
okay,
it shouldn't.
Okay.
Well, I'll think about that.
Any other question? All right, if there is no question, let's thank Daniel again, and thank you very much again for joining us. We are not going to meet next week because it's a spring break in Purdue, but in 2 weeks, we're gonna meet again with Antonio Lerario. Thank you very much and have a good evening.
Thank you. Thank you.
Bye, Daniel. We'll talk soon about our other stuff.
Okay.
Bye.
Bye-bye.